This is introduction to remote data visualization on Compute Canada systems. Mostly, I'll be talking about Cedar and Graham clusters, so our large new supercomputers, but I'll also briefly mention there will be a slide at the end on visualization on the cloud system computers. So my name is Alex Razumov. I'm a visualization coordinator in WestGrid and Compute Canada. And the copy of these slides and all the codes I'm going to show you and the data set as well can be found at this web address. So it's http://bit.ly/remote-cedar. And if you click on it in your web browser, then or copy it into your web browser, it will download a zip file inside of which you can find everything from today's presentation. So today I'm going to talk about two major topics: interactive client-server remote visualization on Cedar and Graham, this one at the top, and also running off-screen batch visualization scripts. So both of these are fairly big topics, and both of these tasks can be achieved using a variety of resources. So you can do these on a cluster's GPU, you can do it on multiple cluster GPUs, you can do it on CPU via software rendering, so as a serial calculation, serial job. And you can also run a impaired parallel job using many processes to do rendering, both for client-server and for batch rendering. So for most of these modes, I'm going to show you examples, and hopefully the clusters cooperate and everything will run nicely. And then I'm going to also talk briefly about VNC. So VNC is a remote desktop solution, and we have some version of VNC installed, but it's not really our full setup yet. So this is going to change in the next few months. And then finally, as I said, my last slide will be about virtual machines on computers. So why do you want to do remote visualization? Well, there could be a number of reasons, but basically the main reason is when your data set is very large and you cannot visualize it on your laptop or your desktop. So for example, you run a very large simulation and it produces multiple gigabytes of output, and then it'll just take a very long time to download all this data to your laptop. And then once you download it, you find out that your laptop simply or your desktop does not have enough memory or enough CPU or GPU power to process this data. So we have fairly powerful machines, fairly powerful computer nodes on the clusters, and why not use these nodes to actually do not just computation, but also visualization. And you can do that fairly easily. There's also a topic called in-situ visualization, and this is something I'm not going to talk about today. This is a totally different topic, probably worth at least one webinar on its own, so we're going to talk about it in the future. So in-situ visualization refers to instrumenting, basically modifying your simulation code to insert some either ParaView or visit library that will make this code act essentially as a server, either ParaView or visit server, to which you can connect from a, let's say, from a client ParaView or a visit client, and then you can guide or steer simulation, and then you can do a lot of really cool stuff. But this is a separate topic, so I'm not going to touch on it today. And then the final bullet point here is commercial software. So if there are some commercial packages installed on WestGrid, so one of them is a very expensive visualization package called Aviso. So we don't actually use it a lot, but I know some people use it occasionally. So in that case, you want to run Aviso on a WestGrid, let's say on a WestGrid system or Compute Canada system, then you actually have to do it remotely. So for most renderings today, I'm going to show this example. This is a standard example I use in teaching, a very simple mathematical function. It's a three-dimensional function of x, y, z in a unit cube given by this equation, and I discretize it on a 100-cube Cartesian mesh, so regular rectangular mesh. And I supply the data set itself. It's called site-envelope.c, so it's a netcdf file inside the zip file that I mentioned on the title page. And I also include into the same zip file the C code to produce this data set. So if for some reason you want to experiment, let's say, with a low resolution and high resolution version of this data set, all you need to do is just compile this code. You can do it on Cedar or Graham cluster, and I should probably include the actual path here. So you need to link the code to the netcdf library, and then run this code, and it will write the site-envelope.c file. Okay, so a couple of words about Cedar and Graham clusters. These are new supercomputers, new high-performance computing systems that went into production in June 2017, so a few months ago. And they are really general-purpose clusters for a variety of workloads, for running large parallel calculations, for running a bunch of serial jobs, for running OpenMP jobs, so pretty much anything you can think of. And they have both CPU and GPU partitions. So GPU partitions can be used for GPU computing jobs, so general purpose GPU computing jobs, and also for visualization. So these two clusters, Cedar and Graham, are located at Simon Fraser and University of Waterloo, respectively. They both have very similar setup, roughly 30,000 CPU cores and several hundred latest NVIDIA P100 Pascal cards. So the specs of these systems can be found in the links on this slide. You can actually open them in the web browser, and there's a lot of useful information there. So these systems have multiple types of nodes. So there are CPU nodes and there are GPU nodes. And both of these have a variety of memory layouts. So starting base nodes have 128 gigabytes memory, and then they go all the way to 3 terabytes. So some jobs require, especially OpenMP jobs, require a lot of RAM on a single node, and that's what these large memory nodes provide. So we run Slurm Scheduler and Workload Manager to manage a very large number of jobs that are always running on these systems. So if you look at the job queue, you will see that there are thousands and thousands of jobs either running or waiting in the queue at any given time, and that is because it's a multi-user system that serves well, both of them are multi-user systems that serve the entire country. So as I mentioned, the software setup is really identical on the systems. All software packages, there are probably a couple of hundred packages listed on the page here at the bottom link. And if you cannot find the software that you want to use there, well, just let us know and we'll be happy to install it for you. So today's talk about visualization, and I'll be talking mostly, so I can hear somebody's mic, so can you please mute yourself? So if you mouse over the video window, you should be able to see a mute button there. Thank you. So I'll be talking about mostly three-dimensional visualization. But some people, well, in many cases, you don't need 3D visualization. So here's just a very brief slide about 1D or 2D visualization. So you can run a bunch of Python libraries or R libraries entirely off-screen on the cluster. So let's say you have a data set, and you just want to do some simple 1D or 2D plots. So in this case, in this example, you can run matplotlib scripts entirely off-screen on Cedar and Graham. And what do you do? So here's an example of a script. I'll call it simple.py. And all it does is basically plots a function of mathematical function of, so it's an exponent, x versus y, and then saves it into a PNG file called compute.png. So the trick here is really to use an off-screen backend. So you'll need to specify, you need to explicitly tell Matplotlib that you don't want to open any window, you just want to run into, write into an off-screen backend using the PNG file format. And then everything will be saved into this file. So this is the script, and this is how you run it on either Cedar or Graham. Simply load the, let's say, Python 2 module. Then you'll need, so we don't have matplotlib installed, but you can actually install it very easily in user space. So if you run this command, after loading the Python module, it will install matplotlib graphics library into the .local subdirectory in a home folder. And then you can simply say Python simple.py, it'll run, will take 2 seconds, and then it'll produce a nice PNG file. So this is for low dimensional 1D and 2-dimensional visualization, and I'm not going to spend any time on this. And today we're going to talk about 3D remote rendering on the clusters. There are many packages for 3-dimensional rendering, especially domain-specific packages, things like VMD, Visual Molecular Dynamics, lots of other tools, really wonderful packages. So these are mostly, these tools are domain-specific. And in WestGrid and in Compute Canada, we try to use general-purpose tools, so not limited to one particular field of science. And there are actually 2 such wonderful tools. One is called ParaView, the other one is called Physic. And both of them are open source under active development, multi-platform. You can download the source code, or you can download a precompiled binary for Linux, Mac, Windows. And basically, they have all these nice features that you see on the slide. And both of these tools have been developed specifically for very large-scale visualization on the clusters, but you can run them on your laptop as well. They support, they have a very nice GUI interface, very different. Visit and ParaView have very different GUI interfaces, so if you learn one of them, it's a little bit difficult to switch to the other. They both support Python scripting. They both support client-server usage mode and so on. Really wonderful packages. So we teach both of these in our various webinars, in our workshops. So in WestGrid, for example, I have standard full-day workshops, one on Visit, the other one on ParaView, and I travel to various WestGrid member institutions. Usually I give several of these per academic year. So basic introduction to Visit or ParaView for someone without any visualization experience or without any Python experience at all. So if you're interested in these workshops, in seeing these workshops at your institution, please let me know, and we'll be happy to organize them for you. So in this webinar, I'm going to use ParaView for examples, simply because there are too many topics and too many examples. I cannot show everything for both ParaView and Visit. But the same general ideas apply for remote Visit visualization as well. So both for ClientServer and for batch rendering. So if you need examples with Visit, let me know, and I'll be happy to supply these to you offline. So for the purposes of this webinar, I assume that you're already familiar with the basics of ParaView. So basically, when you open ParaView, it will give you a GUI similar to this one. You will have the nice visualization panel on the right, and then you'll have the pipeline browser on the left. And then when you click on any object in the pipeline browser, it will display properties here on the bottom left. So basically, you have to know to use ParaView. You have to know how to load a data set, how to switch between different views or different representations. For example, this is a surface view right now. You can switch to points view, to a volume view, or to wireframe view, etc. And also, you need to know how to use filters. And all these topics I teach in the workshops, and you can also find all materials for our full-day workshops in this file. So ParaView, again, bit.ly/paraview.zip contains slides, data codes, and everything else. So if you want to learn ParaView in your spare time, then just download that file and off you go. So a few words on XLM forwarding. In principle, you can log into a cluster. Like in this case, I'm logging into Cedar, and I'm using XLM forwarding. So -Y stands for trusting XLM forwarding. And then you can load the ParaView module, and then simply start ParaView. Let's say on this case on the on a login node of Cedar. And then if you have a XLM server installed on your laptop, so this is installed by default on Linux. On Macintosh, you have to download usually a separate XPlus package. And then there are many different implementations of Windows for an XLM server. So assuming you have it installed, you can simply load the ParaView module, then set ParaView on the login node, and then sometime later, maybe 20 seconds, maybe 60 seconds later, depending on your connection speed and how busy the login node is, the ParaView window will pop up on your laptop, and then you can work with it remotely. You can even do that inside a compute node. So all I have to do is basically start an interactive job using the XLM forwarding flag right here, and then you can load the ParaView module, and then so it has to be specifically this ParaView module that includes GUI, so GUI version of ParaView, and then open ParaView, and then you will be running ParaView on a compute node as part of a scheduled job. So this will work fine, except that it will be very, very slow, and it's just not efficient. And the reason for that is because XLM forwarding was designed back in the mid-1980s, and it was never meant for such really heavy remote graphics. So it will work fine, but it'll just be very, very slow, not particularly responsive. So we don't recommend this solution, although I know a lot of users just use it simply because it's simple, you don't need any special setup. So instead, what we recommend is using ClientServer or bash scripts, and I'm going to talk about this a lot today. So right now, we don't recommend VNC for the reasons that I'm going to outline later on in my talk. So another quick slide before I'm going to show you examples and demos is how to do rendering, OpenGL rendering on a classless GPU. So in general, to use a classless GPU for doing computer graphics, for doing OpenGL rendering, you have to have two things. So first of all, you need OpenGL support in the GPU driver. So all of our cards come from NVIDIA. And pretty much all NVIDIA cards going back 10, 15 years, they support GPU. And also you need an XLM server. So basically, if you go this route, then you will need to have an XLM server that is running on the compute node on the cluster. And then you have to specify the display variable, and then all renderings you do will open into a virtual display attached, well, virtual display because it doesn't really exist, attached to this GPU, and then all rendering will be done on Windows, inside a window running on that GPU. So the problem here is that you need a running XLM server, and for many reasons, we really want to have a fairly streamlined setup on compute nodes, so we don't have full X11 installed. We have a basic version of X11 with very basic window manager, and it also requires a running X11 server. So if for some reason it crashes, then you won't be able to do OpenGL graphics on the GPU. We'll have to contact the sysadmin and ask him to restart an X11 server. So it's quite a lot of hassle. A simple solution, and that is fortunately supported now in the latest version of NVIDIA GPU drivers, is to have what is called OpenGL Rendering context. So basically, a context into which client APIs will draw the pixels. To run this completely not inside the X11 server, but to run it completely, to have it provided completely by the NVIDIA driver. And so for that to work, you have to have the latest version of ParaView and so latest NVIDIA drivers, and ParaView needs to be recompiled with EGL support. So we have a special version of ParaView supplied by this module, so ParaView off-screen GPU 5.4.0, that provides both a ParaView server for client-server connections and a PV batch script for running a batch ParaView scripts. And so unlike with the X11, that actually needs quite a lot of setup to do very high-resolution graphics. So it's a little bit tricky to do, let's say, 4K images for video inside X11 server. With EGL, it's just very straightforward. So I did some tests yesterday, and I just once we asked it to do a, let's say, 4K 3840 by 2160 image, and I'll just do this image without complaining. So it works very nicely. All right, so ParaView, already mentioned client server. ParaView has this distributed architecture. It has three different components inside of it. So when you download a standalone ParaView on your laptop, you will find three components as part of the same application. So there's a data server, a render server, and the client. So the data server is basically a unit responsible for data processing, reading data from the disk, computing, doing some calculations, computing filters, and so on. And the render server is responsible for rendering. And then the client is actually, GUI, very nice interface with, multiple menus and sub-panels and so on. So as I mentioned, when you download ParaView on your laptop, all these three components run inside the same application. But in principle, there is no reason why you cannot run all these as three standalone applications, standalone programs on different computers. So the usual remote visualization client-server rendering setup is that you run this data server and the render server as a single application in parallel, maybe in serial, maybe in parallel on a computing cluster. Then you run a client on your laptop, and then you connect the two, and then you do visualization remotely. All data processing, all data is sitting remotely. All processing is happening remotely, but then you're interacting with it locally on your laptop. So client-server workflow is by definition interactive. That means that to start the ParaView server, you have to start an interactive job. So we have a number of interactive nodes, both CPU and GPU interactive nodes on both Cedar and Graham. So to list these nodes, you can simply run the following command: sinfo, list all Sloan partitions, and then just look for a graph for interact. So that will show the interactive nodes. So let me log in now to Graham cluster. So I have an alias for logging into Graham. And hopefully my fonts are big enough for you to see. So what I'm going to do, I'll simply run this command, sinfo, and then drag on interact. And we'll show the nodes, the partitions for interactive jobs. So if you submit an interactive job, it will go to one of these nodes. So there are nodes with CPUs only, and there are nodes with GPUs. So if you ask for a GPU, then your job will go to one of these nodes, right? And you can see there actually in Graham, there are 1, 2, 3, 4. There are 4 such nodes for interactive GPU jobs. Okay. So if you submit a job to one of these nodes, either CPU or GPU interactive job, you have to specify the amount of time, how much memory you need, and how many processors, how many GPUs, and so on. So your account name, your default role in Compute Canada. And then it will start an interactive job. It basically will return a prompt in which you can type commands. So you can start a ParaView server by running the corresponding command, either in serial or in parallel, and then that will start the ParaView server to which you can connect from the client. So I'm going to show you an example in a few seconds. And then once you're done with visualization, make sure that you terminate the job, or the job will be killed after the maximum runtime limit is reached. Okay, so now I'm going to show you an example. Let me walk through the steps in the slides, and then I'm going to run the live demo. So on Cedar and Graham, you can submit an interactive job. So what I'm going to do, I'm going to submit this job using the salloc command. So salloc stands for asking for an interactive job. Asking for 30 minutes, a single processor, a single GPU, and then I'll ask for 4 megabytes of memory, and then I'll run it under my account, default account. And once the job starts, I will load the off-screen GPU module that I mentioned already. I will unset the display variable. So this might be necessary. This is not always necessary, but it's a good idea to do this to make sure that ParaView does not attempt to do X11 rendering, so that it will actually do rendering using the EGL framework on the inside the NVIDIA driver. And then I'll start the single serial, so single CPU, single GPU ParaView server. So here I don't actually have to specify the GPU index because it's, so by default when you ask for a single GPU, you ask Splunk for a single GPU, it will give you some GPU, one of the GPUs in the cluster, but inside your runtime environment, inside the job, that GPU will have index 0. So you don't have to supply, you don't have to tell the ParaView server which CPU you want to use exactly. But if for some reason you want to use multiple GPUs, you certainly can do that. So when you submit the job, you ask for more than one GPU here, and then you'll have to supply, basically tell ParaView server which of these GPUs assigned to you you want to use for rendering context, for opening essential windows. And then, so once you start the ParaView server, it will return a prompt, not a prompt, it will return these lines, basically saying that connection, we are now live, accepting connections on this node and on this port, okay? And then next thing, what do? You'll need to connect your, basically in a different window, terminal window on your laptop, you'll need to connect your default, default ParaView port, so it's 1111, on your laptop to the same port 11111 on the compute node that is running the ParaView server. And then you start the ParaView client and then connect to local host on port 111. So that's the port where that appears right here in the previous command. All right, so let me try to do this. So what I'm going to do now, I'm going to actually paste commands so that I have to type them, because there are many examples. So let me find the command for starting the single CPU GPU job. So I'm asking for the job. Let's see. Okay, so node 987 has been allocated. So now I'm running inside the job. I can actually access some environment variables. As you can see, there's a whole bunch of them. So what I'm going to do now, I'm going to set unset display. So make sure that ParaView does not render into an X11 server. And then I'll start the ParaView server. Okay, ParaView. Oh, of course, I need to load the module. I forgot that. I'll need to load the ParaView module, offstream GPU ParaView module, and then I'll start the ParaView server. Okay, so now it says it's waiting on the node Graham 987 on this port, waiting for incoming connections. So in a different window on my laptop, I'm going to connect the two ports. So I'm going to connect. And you should keep track of the compute node 987 and the port. I'll need these. I'm going to paste them into this window. Okay, so I organized the SSH port forwarding. And now I'm going to switch back to this window where it says accepting connections. And I will start the ParaView 5.4 on my laptop. So notice that it has to be roughly the same version of ParaView as on the cluster. So it's 5.4 point something, right? The same version on my laptop. And then what I'm going to do, and actually I'm not 100% sure whether this will work now, so there is I'm going to mention in a second. I'm going to basically connect to localhost 1111, right? So let's try to connect. Okay, and it seems like it worked. So great. So now we're connected, and it gave me a warning message, so don't pay attention to that. So it's working now. And what I'm going to do next, so this is ClientServer ParaView. The server is running on the compute node as part of a scheduled job on Graham cluster. And the client is running right here on my laptop. I'm going to open a file. And so notice that now when I open a file, it's not my laptop's file system, it's actually the file system on Graham. So I'm going to go into my home folder on Graham. We'll go to a directory called remote, and here I have my data set that I mentioned before, sign envelope.nc netcdf dataset. I'll need to tell ParaView that it's a netcdf files generic dataset. Hit apply, and the dataset was loaded. So let me do a couple of very quick visualizations. So these are remote visualizations. All rendering is done by the cluster's GPU. I'm going to switch to a service view, and I'm going to render, I will color the dataset by density. So here we go. And then hopefully you can see maybe there is a slight delay in your video window, so I can't really tell. And then I'm going to draw a couple of isosurfaces. So I bring up the isosurface filter or contour filter. Let's draw an isosurface at the value function of 0.1. So hit apply. And again, all rendering is done on the cluster's GPU. Here we go. Let's try an isosurface at 0.4. Okay, so here we have a different isosurface. Maybe there's some delay, maybe 10-15 seconds delay in your video window, so I can't really tell for sure. But for me, it works really nice, very smooth visualization. I can interact with it. So there is one setting that is really, really important in client-server mode. So if you go into ParaView, Preferences, and it's actually mentioned on the next slide as well, and go into Render View, so ParaView Preferences, then Render View, and if you scroll down, so your gear icon, Advanced Settings has to be enabled. And then if you scroll down, there's a setting that is called, let me find it, called Remote Parallel Rendering Options. So the default value is 20 megabytes. And basically what this gives you is a threshold beyond which all rendering will be happened remotely. So basically everything that is under 20 megabytes is done locally on my laptop. So you can see that I can interact, so I can rotate the data set very easily. And that rotation is happening locally on my laptop. So the initial rendering was done on the GPU. But basically the idea is that anything that is larger than 20 megabytes will be rendered on the cluster's GPU. Anything smaller than 20 megabytes will be rendered locally. So if I were to set this, let's say, to 0 megabytes, which I can do, and then I click OK, and then if I try to spin the data set, it will be very, very slow. And the reason for this is because even rotation will be done on the cluster's GPU. So it will be rendered on the cluster's GPU, and then it will have to be shipped to your local, to your client, to your laptop. And that might take some while, might take some time. So this setting is very, very important. In some cases, you might want to set it to 0. Maybe your laptop is just too slow, or maybe you just don't do a lot of interaction. If you do a lot of interaction, then it's probably a good idea to leave it just at the default value or set it to something similar. But basically, play with it and find what works for you. And let me know if you have any questions about this setting. All right. The final thing that I'm going to do in this rendering, I'm going to do the volumetric rendering. So I'm going to delete the contour filter, and I will go into the volumetric view, and I'm going to render this as a volume. So I'm going to go to Edit Color Map, and we'll switch to a different color map. So I have a predefined color map, which I will show you how to set in a few seconds. So I just choose one of these, actually all the same. Predefined color maps and close this window, and you can see that I have a nice volumetric rendering showing my function. So this is what I'm going to do in the subsequent visualizations on class. Actually, yeah. So here we go, and then I can actually spin, and the initial rendering was done on the GPU, and then when I spin it, I think it's done on my laptop's GPU. So this is in client-server mode using the cluster's GPU. Okay. So a few important points, as I mentioned already. The client and the server must have the same matching major version. So make sure that if you load it, if you're using the 5.4.0 module on the cluster, make sure that you're using one of the 5.4 versions of ParaView on your laptop. So occasionally you might get this error, only EGL 1.4 and greater allows OpenGL's client API. So what this means is, actually I'm not 100% sure how this error comes about, but basically it means that the NVIDIA driver is not loaded properly, so something happened to the NVIDIA driver, so basically the compute node needs rebooting. And in this case, let us know if you see this error, and we'll ask the sysadmin to reboot the corresponding node. So I already mentioned about the remote rendering threshold, which is very, very important. Okay. So next, I'm going to talk about doing client-server software rendering, and for that, I'm going to close my. Actually, I'm going to disconnect from the server, from the remote server, so back to the original ParaView on my laptop. Then I'm going to quit. So notice the window where I had SSH port forwarding. So I'm going to close that, and I'm going to log out of Graham. Actually, terminate the job, then log out of Graham. And I'm going to go to the Cedar cluster now, so different cluster, but all IDs are the same, so exactly the same setup, same partition, same software environment. And what I'm going to do next, so I'm going to walk through the slides now. I will allocate so I'm going to start an interactive job. This time, it's not going to ask for any GPU, so just a CPU rendering job. Then I'm going to load a different module. So this time, we're going to use a ParaView 5.3.0 module, off-screen module. This is not for GPU rendering, but this is for off-screen rendering on a GPU. So entirely software rendering on a regular processor. And then I'm going to I'm going to start the ParaView server, ask it to do Austin rendering by software, and so specify Mesa, SWOR, AVX2. So what this means is basically it's one of the options that will ask ParaView to do software rendering via a recent Intel library called OpenSWOR. And this library is actually really, really efficient for doing rasterization in software. And then, so the ParaView server should hopefully will start, and then I'll need to organize SSH port 40. And then on my laptop, I'll go to the ParaView client and then try to set up the client server connection. So let's do this. Once again, what I'm going to do now is I will start a job, this time on Cedar, and not asking for any GPUs. So it's a purely CPU rendering job, an interactive job, and then it went to this node 544. So let's see if this works. I'm going to load the off-screen version of ParaView for CPU rendering, and then I'm going to start the ParaView server on this node. So it should say, yeah, accepting connection. So Cedar 544 on this port. Then I'm going to go on a different into a different window on my laptop, and I'm going to run the SSH port forwarding command. So it's which node was it? 544, and I'm going to type it here. So 544. Okay, so SSH port forwarding is done, accepting connections, and let's now try to connect. So I'm going to again go to click on the remote link, and notice that here what happens, they give me an error message. So let's see. Yeah, that's my mistake because I need a matching version of ParaView. So I'm running 5.4 on my laptop, and what I really want to do is I'm going to restart the ParaView server here. And I'm going to start ParaView 5.3 on my laptop. So that's very important. Okay, so let's try to connect. And here we go. So we're connected. And now I'm going to attempt some rendering. So again, I'm going to load. So this time we're running on Cedar. I'm going to the Cedar file system. Going to click on remote, load the same sign envelope function, and let's try to do volumetric rendering. This time we're doing rendering entirely in software. There's no GPU on the cluster, on this node. And let's try now to load the different color map. Okay, so here we go. We're doing rendering in software entirely on the cluster. So this was done using a single processor. So we can actually do multi-processor rendering as well. So I'm going to show you the demo. This time, so I'm going to disconnect from the server. And okay, so to disconnect from the server right here. And then I'm going to go in here and so we're back on Cedar. Let me log in back to Cedar. Oh, sorry. Not this command. I just want to log into Cedar. And what I'm going to do now, I'm going to start a job asking for 4 CPU cores. So, okay, so the job started. And actually, the job is running on the same node as before. So I don't have to retype this command. So I still have the SSH port forwarding running for the node 544. On the, to the port 11111, the port ParaView port. So okay, so now I'm running a job, a parallel job on the 4 CPU cores. And next I'm gonna, so let's see if I have the ParaView server. Okay, so I need to load the module to make the server accessible. So for that, I'm gonna again load the module. And then I'm gonna copy and paste the command. So now this is a parallel server running. So srun to make sure that I'm starting an API parallel job, ParaView server is an API job, using Austin rendering. And now I will try to connect to the same node from my ParaView, same port on the same node from my ParaView, and let's see if this works. Oops. My ParaView is hanging for some reason, so I'm not sure what's going on. So I'll probably have to kill it my local ParaView client is setting. So I'm going to go to force quit, and it's not responding. I'm not sure what's going on. So I'll quit it, and let's try it again. So I'll start ParaView 5.3. Here it is. And let me connect. So we have port forwarding. Actually, let me organize. Maybe I was not running port forwarding. Yeah, I think I'm not running port forwarding. So let me do it again. So double check. Yeah, 544 is waiting for incoming connection. And I'll do port forwarding to 544. Okay, I think I just didn't organize port forwarding. So let's see where it says waiting for incoming connection. Let's try to connect. Okay, so now we're connected. I think I just didn't do port forwarding correctly. So, and now let's try to load the same data set. So go to File, Open, navigate to the remote folder in my home directory on Cedar cluster, open the same file, so it's not Cedar files generic, hit Apply button. I'll switch to the surface view, switch to coloring by density. So this is the familiar view. And now what I'm going to do, I'm going to pass the data set through a filter called Process Scalar ID. So Process ID Scalar, sorry. And what it will do, it will associate a unique scalar variable that will be equal to the ID of the processor on which the corresponding subdomain is rendered. So we'll see what I mean in a second. So I'm going to apply this filter, and then I'm going to again switch to surface view, and I will ask it to color by the process ID. And as you can see now, we're actually doing rendering in parallel, and there are 4 processors, so each processor is responsible for rendering the corresponding subdomain. And you can actually have some fun with it. So for example, what I'm going to do next is I'm going to add a glyph filter, so make sure that I add spherical glyphs, and I'll just draw 5,000 random spherical glyphs. And I will ask them to, so where it says scale is a process ID, I want to switch to scalar density. I will turn on scalar mode, and then the scale factor, set it to something smaller, let's hit 5. So when I hit apply, you'll see what's happening. And let me make the process ID scalars a little bit more transparent. So I'll change the opacity. There should be a slide of opacity right here. So you can actually see inside the volumes. Yeah, here we go. So this is more or less the effect I was going for. And then we need to, so the three-dimensional blocks are colored by the process ID, so basically by the ID of the processor on which that subdomain is rendered. And I'm going to use the same color for the glyphs for the spheres. So color spheres by the process ID. Yeah, so this is the effect I was going for. So now we have a visualization where each subdomain is processed on one of the 4 processors, and the spheres are also processed on one of the 4 processors, and then the radius of each sphere, so these are 5,000 randomly dropped spheres, and the radius of each sphere is proportional to the value of the function at that point, and then the spheres also colored by the process ID. Okay, so next what I'm going to do, yeah, and so by the way, I haven't mentioned it, but if you were to time this, you'll actually see that now, since we're doing rendering in parallel, it's actually a little bit faster. It feels faster than doing this in serial. And then optionally, we can run it on, let's say, 30 cores, or how many cores you want to throw at your big rendering job. Okay. So I promised to mention VNC very briefly. Right now, the problem with VNC is that not all hardware is set up, has arrived, or has been set up properly yet, because the clusters went into production a few months ago, and the system teams were really, really busy with, just figuring out the basic problems and making sure everything works. So the plan is on Cedar, setup will be slightly different. So on Cedar, so right now we have a single login node, and more login nodes will be added later on. And one of these new login nodes, none of them have GPUs, so it'll be all software rendering. So one of these nodes will be converted to CPU rendering, so we'll install the software stack, the X11, full X11 libraries, a nice window manager, and then it will have a secure VNC setup. So that means that basically all you need to do is start a VNC client, you point it to this special visualization login node, And then it will, inside VNC, it will ask for your Compute Canada username and password. And then once you supply this, you'll have your nice remote window, the remote desktop window into which you can open multiple windows, including ParaView or Visit window, and then you'll be doing your visualization. So this will be done in the next few months. Right now, the setup is not there yet. So on Graham, the setup will be similar, except that these special visualization login nodes will have GPUs on them, and these nodes, I know either they have just recently arrived or they're still on their way, but they will be added to Graham in the next few months. And again, we'll have a secure VNC setup that will handle user authorization, so authentication, so you don't have to start a VNC server by hand yourself. So everything will be fairly much automatic. So the only difference between Cedar setup and Graham setup will be that Cedar will be running on CPU nodes, so it will be software rendering for a ParaView Visit, and then on Graham is going to be GPU-based rendering. So right now you can use VNC on Cedar and Graham, but it's not the setup I want to advertise. It's actually very clunky. So the idea is that you would start a compute job either on a CPU node or a GPU node. Then you will start a VNC server as part of the compute job. Then you'll run VNC port forwarding between your laptop and the compute node. But it's a little bit clunky, and also the window manager and XLM setup on the compute nodes is not very good. So I don't recommend this setup. It's going to be very slow. It's going to crash a lot for you, and it's just going to be very hard to use. So instead, for interactive use right now, I recommend ClientServer, and then in the next few months, we're going to add the VNC setup to that as well. So the ClientServer, as you saw, works really nicely, and it's just very usable, very fast. So the second big part of my presentation, and I see I have only 15 minutes left, so I'll try to go through it briefly. Maybe I'll skip some examples, is off-screen batch rendering with scripts. So the idea of batch rendering is that you prepare a visualization script that will run completely off-screen, so it doesn't open any windows. And then you'll run it remotely on the cluster. So your data set is sitting on the cluster, and then you're doing all processing, data set processing, and rendering on the cluster as well. And you can do it in many different ways. So you can use a CPU, you can use multiple CPUs, do it in parallel, you can use a GPU or multiple GPUs. And so the idea of this is if your visualization is very large, it takes very long for rendering job, let's say, I don't know, hours or maybe even days for this rendering job to finish. Maybe you can run it in parallel on the cluster as a background, as a regular compute job, and then come back, in a few hours or maybe the following morning, and your nice movie will be ready. And of course, this batch rendering, this scripting is also really useful for automating repetitive tasks and produce animations where you have multiple frames. Let's say in a time-dependent simulation, multiple time steps, and you do an interactive visualization for just one time step, and then let's say you have 2,000 time steps. You want to do exactly the same type of visualization for each one of them. So just write a script, submit it as a background compute job to the cluster, and then come back a few hours or the next day, and your nice movie will be ready. So what I want to mention here is that it's not only ParaView and Visit, but pretty much any Linux tool, Linux 3D visualization tool or 2D visualization tool that has a programming interface that is scripted or compiled language. These can be scripted as a batch job on the cluster. So if you need any help with this, let us know, and we'll be happy to help you. So here I just mentioned some of these tools. So VMD, for example, Visual Molecular Dynamics. It provides Python and TCL interfaces for scripting. So a few other tools. So I'm going to show you examples in ParaView only today. So ParaView does scripting in Python. So there is a special ParaView library that you can load, and then you can run ParaView Python scripts. So to provide, as I mentioned in my in various webinars and my in-person workshops, you don't really need to know any Python to write a ParaView Python script, because there is a built-in recording tool. So all you need to do, and I'm going to show you this to you. So here we have a client-server ParaView running in parallel on the, so this is the client on my laptop, and then the background server is running in parallel on the cluster. So what I'm going to do now, I'm going to delete this data set, not disconnect from the server, because that will disconnect me from the parallel server. And then I'm going to start the go-to tool, start trace. So start recording, for example, just accept the more or less a default dialog settings, and then so I turn on recording, and then I'm going to load the data set. So again, it's the size-and-load function, load as a netcdf file, hit apply, and then just do some basic rendering, for example, surface view, and then call it by the density, and then do a little bit rotation, maybe, I don't know, zoom in a little bit. So what I'm going to do next is I will go to Tools, Stop Trace, and as soon as you do this, this will open a window with a Python script inside of it. So this Python script just corresponds to exact commands that you did in the GUI. So basically you can see that we loaded everything from a ParaView.simple module, then we open the data set, and then we are coloring by density, and then we are doing rotation at the very bottom. So these lines basically correspond to our rotation, right? And so this way you can simply save this as a Python script and then run it off screen without opening any windows. And so in ParaView, there are at least 4 different ways you can run a ParaView Python script. So one of them is to go inside ParaView's GUI, go to Tools, and then Python Shell. And then so it opens the Python Shell. Then you click on the Run Script button, and then navigate to the location of the script, hit OK, and it will run the script for you. Another way is to run this from the command line. So simply start ParaView and say -script is equal to the script name, and this will run this script also offline or maybe opening windows. So depending on actually it will most likely probably will open windows for you. So you can also start a Python shell simply inside the terminal. So say PV-Python, that will not open the ParaView GUI. This will just give you the ParaView Python shell into which you can copy and paste commands. And of course, you can copy and paste commands into this shell as well, right here in the GUI. And so finally, which is relevant to us, if you have a script that you already debugged, all you need to do is simply say pv batch -- use off-screen rendering so that you make sure no windows are open. And so this is very useful for running scripts completely off-screen inside, well, in a cluster, right? So you can submit it as a regular batch job, and it will do visualization very nicely for you. So I prepared 2 scripts. One is called static.py for doing the volumetric rendering I showed you before, and the other one is, so the volumetric rendering, this one. So the script for that is called static.py. And you can also find the script inside your zip file that I mentioned on the title page. And then the second script does visualization, the rendering, the 4-processor rendering that I showed before. So that script is called cs.py. All right? And so to run the scripts, all you have to do is basically, well, so in the first example, here I'm showing how to run a GPU job. So here we are, actually, no, sorry, this is not a GPU job. This is software rendering, right? So rendering on a CPU in serial. So what I'm doing here, I'm loading the, on Cedar, let's say on Cedar, I'm loading the ParaView off-screen 5.3.0, so for software rendering, ParaView module. Then I'll go into the remote directory. And actually, so I still have a few minutes left. Let me try to run this demo. So let me pull up my notes for this demo so I don't have to type all commands here. So again, I will close my ParaView client here, and I will exit Cedar and I'll exit Cedar here as well. So I start with the clean setup. So I'm going to go to login back to Cedar. All right, and then I'm going to submit a job asking for a single processor, 2 gigabytes of memory, and no GPU. So it's a single processor software rendering job. Okay, so it's an interactive job, Salog. It gave me a prompt on the Node 544. So next, what I'm going to do is I'm going to load ParaView, off-screen ParaView. I'm going to go into my directory. So I want to make sure that I don't have any, and I don't think I think I have already erased all of them. So there are no PNG files. And next, what I'm going to do is I will, so the script is right here. I'm going to simply do more on it. So here's the script. So it will load the data set. And at the very bottom of the script, it will write the output into the file called volume.png. There is no such file as you can see. So there's no file volume.png. All right. And now I'm going to run the script. So the command for that is pv bash use off-screen rendering followed by the script name. Okay. So now it's running, and now we're running inside the interactive job. So of course, this is purely for testing and for debugging, just to show you that this works. I mean, really what I want to do to submit it as a non-interactive job, right? So the script ran, it did not complain. So let's see if we have now the file volume.png. It was just created, right? And so to see this file, I'm going to copy it to my laptop. So what I'm going to do, I'm going to simply bring up the secure copy command. So from Cedar, I'm on Cedar. Yes, I'm going to copy from remote directory, I'm going to download the volume.png into the current directory. Okay. So this is the file I just rendered half a minute ago on Cedar. And here's the file set. Open it. It just went to a different window, a different screen. So here we go. Here we have the rendering that we did completely off screen as part of an interactive job running the script without opening any windows in the cluster. All right. So, of course, it's useful to do it as a serial batch non-interactive job. And the idea is the same. So basically now, what you do is, let's go back to the cluster. So here we're running an interactive job. I will exit the job. And then I will submit a, let me go back to my notes, it's page 26. Let me submit a, so I'll make sure to erase all files. Actually, let me CD into the remote, erase all files. And then load, can't remember if I loaded. So load the off-screen software rendering ParaView module. And then let me submit a batch job. So the script for that is going to call s1.sh. And you also have a copy of the script. So all scripts, I'm going to show you Python scripts and shell scripts are inside the zip file that I mentioned on the title page and downloaded. So the shell script is called s1.sh. As you can see, it simply runs a batch job. So I'm not asking for, I'm not specifying the number of CPUs. So the default is 1. So you're going to submit a serial job, asking for 5 minutes. So job name, asking for 2,000 megabytes, and then my default queue, account name under which I'm submitting, and here's the command I'm running. So it's the same command, pv batch, use off-screen rendering on static.live. So let me double check that I loaded the module. Yeah, so the ParaView off-screen module is loaded, and now I'm simply going to submit the job. So I'm saying batch s1, and it will run. So submitted the off-screen job. So the job is running. As you can see, it will take maybe 10, maybe 20 seconds. It will write an image file, and then it will exit. So let's just wait a little bit. Okay, so it finished running. We have a file volume, oops. Oh, it did complain. Maybe it didn't work, so let's see what's wrong. Oh no, it complained, it didn't work. So, and the reason for that is, okay, so it didn't work this time. This is unexpected. Non-existing physical address. So we've run a single CPU job, and I submitted the right script, right? So the script is as batch. I'm not sure what went wrong. So I think a bus error. I think this is just a runtime error. So something is wrong to the node, the runtime environment. So not sure. Let's try it again. Let's just submit it again and see if it works. Maybe we'll go to a different node this time. Okay, so let's do more on the latest job. So that's the output file. No, it simply went to, not sure. So we'll need to debug this, sorry. But it ran yesterday without any problem. So this is the first time I actually see this problem. But the problem here is that it is, actually, let me try to do this on Graham and see if it works. So the problem is there's something wrong on the node. So maybe the node needs rebooting or something, and then it just goes to the same node. So let me try this on Graham. So on Graham, I'm going to go to this directory, same directory, I have exactly the same setup. I'm going to load the off-screen rendering module right here. And then I will, so here's the batch script, and then I will run this batch script. Let's see if it works now. Okay, so the job is running. Okay, so the job ran, and the output file does not contain anything, so there are no error messages. And then there is the file volume.png. So now you can actually see that it worked. And now if I go back in here and I do async from now, this time from Graham. So I'm downloading volume.png from Graham cluster. So here it is, the new version. And here's the file. So now we did off-screen rendering entirely as a batch job without opening any windows, as a regular serial batch job on the cluster, on Graham cluster. Right? So I have quite a few more slides, and we are running out of time, so I'm just going to show briefly, without running in demos, what I have in these slides, and then I'll open the floor for questions. So in the next slide, I'm showing how to run a parallel job. So there is a script. There are actually three scripts: P1.sh, P2.sh, and P3.sh. And these are, so the first one will produce volume.png. The second one will produce the spherical glyphs. Remember the picture, when I ran it on 4 processes, it gave me 4 subdomains with spheres embedded into those blocks. So that's running on 4 cores and on 8 cores. And then you can download the picture to your resulting picture regions.png to your laptop and verify that it indeed ran on 4 and 8 cores respectively. Here is how you do GPU batch rendering on Cedar and Graham. So the idea is very the same. It's very similar to the interactive job, except that now you're submitting a script. So I have a sample script GPU.sh that should work. You simply submit it. So you load the module before submitting the job. So this time you load the off-screen GPU 5.4.0 module on Cedar or Graham. You submit the job, and then inside the job we're calling static.py. And then it should do all rendering inside, on the GPU. And then, so inside the script, you also need to set the display variable to make sure that rendering is done by the EGL framework on the NVIDIA, inside the NVIDIA driver. All right. So here's how we can extend the script. So unfortunately, I'm just running out of time. But here's this nice example of how we can do visualization. So this visualization would do rendering, and all the scripts work, so you can actually copy and paste them and then just copy them onto the clusters and try to run them. So in this case, we are replacing the output line save screenshot with the following line, and this will rotate. So this will produce 90 images. Each one of them is a rotation of your visualization of your object by 1 degree relative to the previous image. And then, so you do that, you can run this as an off-screen batch job on the cluster, and then you run it, and then so the output will be 90 images called frame 0000 to frame 0089.png, and then we have a nice tool ffmpeg installed on the cluster. So you just run this command on the cluster, and this will produce a nice movie. You can download this movie and then watch it on your laptop. So I'm going to skip the rest of the slides. Basically, so here's how to do visualization inside a VM on the Compute Canada cloud. So we have a full documentation running both ParaView client server and Visit client server on a VM. But the idea of VMs is that these are managed by users themselves. So all you do is you request resources, the VM starts running, and then you'll have to install, compile, Visit, and ParaView yourself. So we have full instructions for that on the web page. So there's a link right here. And then if this is something that you are interested in, then please go ahead, and any questions, let me know. So finally, last slide. What I'm talking about is interactive and batch jobs. So these are really orthogonal decisions. So which one you do, interactive or a batch job? So the idea is interactive jobs started in client server, and this will give you interaction where heavy lifting is done by the remote machine, and then we see interaction on your laptop. But this is only good for for quick visual analysis, but not for doing any sort of heavy rendering that takes many hours to finish. So for that, you really want to write a script, a ParaView, let's say ParaView Python script, and then submit it as a batch job. So another option that you should be aware of. So if for some reason, I don't know, the batch job scripting doesn't work for you, and you still want interactivity, but your data set, let's say, very large, then another thing you can do, you can try to downscale your data set, then do, let's say, remote client-server visualization, or maybe even download this scaled down smaller version of the data set to your laptop, then do full interactive visualization on your laptop, and then write the Python script, then copy this Python script to the cluster, and then run it in batch mode on the original full-scale data set. And then you will have the exact visualization that you want to do, but it will be very large rendering. And then the other decision that I have to make, so CPU versus GPU. And there's no single good recommendation here. So for some things, running on the GPU is better. for some things running on a CPU is better. So a few remarks here. So sometimes a GPU might not be available. So we will have several interactive GPU nodes that are available for this sort of work, but sometimes people just run, either use all of them for visualization or just submit regular compute GPU jobs to them, and these nodes just might not be available. So in that case, just switch to CPU rendering using the recipes that I showed you before. And so CPU rendering, sometimes it's slow, sometimes it's fast. So there are a couple of new libraries. One is called Osprey, the other one is OpenSPOR. So one is from ray tracing, the other one is software rasterization. And for some types of visualizations, they're actually surprisingly fast. They're comparable in speed to GPU rendering. So that's all I want to say here. So my last slide is just open the floor for questions.